Now, the 21st birthday problem which I had taken in the previous session may not be easy if I wanted to know the total amount I collect at the age of 99 or at the age of 87. If the value is big, then continuously adding up each of the pocket money I get on that respective year may not be an easy task. Therefore, if the numbers are very large, then random addition of all the terms of arithmetic progression is not possible. So let's find a derived formula through which we can find the sum to n terms of arithmetic progression for however large n is. Let's derive a formula. So in order to derive the formula, the credit goes to the mathematician Gauss, where he has invented a method of finding the sum to n terms of arithmetic progression using the Gauss method. So let's see the Gauss method of finding the sum to n terms of arithmetic progression. So in order to do that, let's consider the general arithmetic progression which we have already discussed in the previous sessions. So the general arithmetic progression here is identified to be A plus D, A plus 2D, so on and so forth. Finally, leading to the nth term A plus n minus 1 times D. So for this general arithmetic progression, A plus D, A plus 2D and A plus n minus 1D, so on and so forth, I just take the sum because I need to find sum to n terms of arithmetic progression. Now these are the n terms of arithmetic progression. I sum up and denote with S. The sum S, when you add each of A plus D, A plus 2D, so on and so forth, is what we get when we sum up each of the terms up to nth term. Therefore, when I take S as sum of each of them, I would like to derive a formula for this. So in order to derive the formula for this, I take this as equation 1, and finally what I do is I retake S, but in the second case I arrange the terms from last to the first. I arrange from last to the first term. Therefore, my first term is A, therefore the last term becomes the first term out here. So I get A plus n minus 1D as the first term, and then the term before this being A plus n minus 2 times D will be the second term of the given second expression. Similarly, the third last term, that is A plus n minus 3D, will be the third term of this, so that finally I get the last term here as A, because the first term of this comes out as the last term, and then this is taken as equation 2. So this is how I arrange S in the reversing order of last term to the first term of equation 1. Then what I do is I just try to take these two equations and add them up, because let's see interestingly what happens when I add each of the sequences. On the left side, when I add, I get S plus S is 2S, and then when I add each of them, I take into consideration that I add this pair, and then I add this pair, and then I add this pair, respectively each of the pairs being added separately. Therefore, when I add this with this, I get 2A plus n minus 1 times D in case of this, and when I add this also I get 2A plus, this is the first term, and then I get 2A plus D plus n minus 2 of D, and then when I add this I get A plus 2D plus A plus n minus 3 times D, so on and so forth. I get A plus of this. This on further simplification gives me 2A plus n minus 1 times D, where this when simplified gives me 2A plus D plus nd minus 2D, which gives me minus D. So again I get 2A plus D minus 2D is minus D, So 2a, again I re-simplify this, I get 2a plus n minus 1d, because when I take d common I get 1 plus n minus 2, which is n minus 1. Again this gives me a plus a, which is 2a, and this further taken in place gives me d common, n minus 3 plus 2 is again n minus 1. So therefore this also gives me an equal term, n minus 1d. So I observe here each of the terms when simplified gives me the same term, 2a plus n minus 1 into d, 2a plus n minus 1 into d, 2a plus n minus 1 into d, and so on and so forth. I get here 2a plus n minus 1 into d. So I get all equal terms until I reach to the last term, which are equal. Now I observe here there are n terms which are coming from here to here. There are totally n terms. Therefore, when I multiply 2a plus n minus 1 into d n times, I get 2a plus n minus 1 into d times of n, because since there are n terms, each of the term added n times gives me n times of the common term, since there are n terms. Therefore, I get here 2s is n times of 2a plus n minus 1 into d, so that my s is, when arranged, n by 2 into 2a plus n minus 1 times d, which is called the sum to n terms of the arithmetic sequence given by the formula. So this is how I understand the sum to n terms of arithmetic progression is given by n by 2 times 2a plus n minus 1 into d, is how we get the derived formula using the Gauss method. So this is the Gauss method of finding the sum to n terms of arithmetic progression using the reverse process, the derived formula out here. So the sum to n terms of AP, which I have generally derived here, is generally denoted with Sn or S, because Sn stands for the sum to n terms. If I say S5, it denotes sum to first 5 terms. If I say S3, sum of first 3 terms, etc. So the derived formula was n by 2 times 2a plus n minus 1 times d. But if I want to express this in the nth term form, then let's see how we can derive this into the nth term form. As I remodify this, I get here n by 2 times 2a. I can split it as a plus a, so that this can be written as it is down here. So this is split as a plus a. Next, I get this as a plus n minus 1 into d is identified to be the nth term an, which we already discussed, since here an is the nth term. An is the nth term of arithmetic progression. Therefore, also I have a as a1, because the first term a is generally denoted with a1 plus an is what I get for Sn. More in general words written as n by 2 times first term plus last term is how I derive the formula for sum to n terms. So if I'm given the first term and the last term, or the first term and the nth term, I can straight away use this formula as an extension of the previous derived formula. So this formula is exclusively used only when the first and last terms are given in the problem. Other than that, if my common difference in first term is given, I use this formula as derived in the previous case. So this is an extension of the derived formula. So let's see the notation for sum of first n terms as we have derived the basic formula. Let's recap in detail out here. So with the conclusion, we make that the sum of first n terms of arithmetic progression is generally denoted by Sn is given by the formula n by 2 times of 2a plus n minus 1 into d, or it is also given by the formula Sn equals number of terms by 2 of first term plus the last term. So we can use either of them depending on the last term is given, I use this formula, or Sn is given, I use this formula, where each of the notations are given. We know that A is the first term, D is the common difference, N is the position or the number of terms of the given arithmetic progression is how we derive for sum to n terms of AP. Now let's see some example problems supporting the derived formula. That is, say for example, I wanted to find the sum of first 7 terms of, say the pattern is -1, 1 over 4, 3 over 2, and so on. Now in case of this, I would like to find the sum of first 7 terms. So let's identify this to be, let's examine this for an arithmetic progression. So as I clearly see here, the pattern is -1, 1 over 4, 3 over 2, and so on and so forth. The common difference here is 1 by 4 plus 1, which is 5 over 4, and the common difference here is 3 by 2 minus 1 by 4, which on simplification gives 6 minus 1, which is 5 by 4. So this is an arithmetic progression because the common difference is same. This is an arithmetic progression. Now for this arithmetic progression, I wanted to find sum of first 7 terms, which is denoted by sum of first 7 terms is denoted by S7, and therefore we have the formula for Sn where n is equal to 7. So let's take the formula for Sn and then substitute n equal to 7. So as I already have Sn equals n by 2 times. Now here the last term is not given out here, therefore I don't take the second case of the formula, but since the first term and the common difference is given, I take the general formula 2a plus n minus 1 times t, where my n is 7. In this case, n is 7 and my a is the first term, which is -1, and my common difference is the difference of this term with this, which is 5 over 4. So substituting the values of n, a and d in the Sn formula, I get the sum of first n terms, which is S7. So let's see how we can substitute each of them.